Hello. Greetings to all. Dear my friends, ladies and gentlemen, welcome to this episode. This is the second part of DC motor. So in today's lesson, we are going to deal with the shunt DC motors and the series DC motors. These are the self-excited DC motors. So last time, if you remember, we have been discussing about the separately excited DC motor, and we have been discussed also about the permanent magnet DC motor. So in our today's lesson, we are going to discuss about the self-excited DC motor. As you know, this self-excited DC motor can be classified into three categories. The first one is a shunt DC motor, and the second one is series DC motor, and thirdly, the third one is a compound DC motor. So let's get into it. So in our today's lesson, we are going to deal with the shunt one first, and then we'll proceed to the series one DC motor. So under shunt one, we are going to discuss about the equivalent circuit and the analysis part. We are also going to see the performance characteristics of the shunt machine, and finally we shall see the speed control of the shunt motor. So let's get into it. Here, unlike the case of the separately excited, as you remember, in separately excited DC motor, we have two separate DC power supply, one for the stator or the field, and the other is for the rotor or for the armature. So in separately excited, we have two separate DC power supplies, but here in self-excited, we only have one DC source. So that single DC power supply will be given to the stator part or the field winding, and the armature part or the armature winding. And the armature and the field windings are connected in parallel to each other. Therefore, it is quite easy to make DC analysis. And as usual, we usually ignore the inductance value. So because of this is a DC analysis that we have been discussed earlier, so that you can easily analyze this circuit by Kirchhoff's current law. So this is a total current. And this is the field current, and this is armature current. So as you can see here, the total current equals the field current plus the armature current. And the field current, this current, equals, because this is a parallel, therefore the voltage across, since the total voltage is a VT or V terminal voltage, so again, the voltage across this is exactly the same as the voltage across this. So this is exactly equals with V terminal. Hence, the IF or field current equals VF divided by RF, and this constant. And when you come to the armature, RA is also VF divided by RA. So the shunt motor is categorized as a constant speed motor, the same as that of the separately excited motor. In separately excited motor, it is almost a constant speed motor, except it depends on the load. But when we see all the DC motors, might be shunt or series or might be separately excited, they are load dependent. The speed of DC motor usually depends on the load. If the load significantly increases, the speed will be drawn or it will be decreased. Therefore, all the DC motors are load dependent motors. That's one of the disadvantages of DC motor. So So, however, the torque characteristics of the motor depends on the load that we have been talked earlier. As long as the load is constant, again, the speed is remain constant. The same is true for the separately excited as well. However, when the load increases, the speed of the motor dramatically reduces. So these types of motor is used whenever stable and exact speed control is required. Now let's come to the characteristics of the DC motor. First, let us see the speed versus IA armature current. So from this, the speed equation, this is a speed of equation. So VA speed equals VA minus IA RA divided by KIF. So from this, VA is constant, KIF is constant, and again RA is constant. So this is something look like a constant curve. So as you can see, this is a constant curve. So as long as the I armature increase, the speed remains constant. This is true in case of there is no any load connected to the shaft or in no load state. But when the load is connected to the shaft, this will no more work. That means if the load increase, the speed will decrease, that will be mentioned earlier. So at the load increase, as the load increase, IA, the armature current also increase and the speed decrease. So at no load it is constant, but this is almost seems constant, but it's not constant. It's usually depend on the load. This is the speed versus armature current characteristics of DC shunt. Now let us see the torque versus armature current characteristics of DC shunt. Now from the torque equation, torque is directly proportional with the armature current. So the curve is obviously it's a linear curve. It's a linear curve. This is the electrical torque, the developed electrical torque. This is mechanical torque or shaft torque. So it's not exactly the same as with this because of there are a windage and some frictional loss are there. So it's not exactly the same as with the developed torque. Well, let's continue. And the third characteristics of the DC shunt that we are going to see is torque versus speed, very important. As you can see, this is the torque. Torque equals K flux. By the way, when I say flux, I mean it is the same as with I field, the field current. So I interchangeably use the flux and the field current. So sometimes you can consider that when I say flux, I mean this field current. So torque equals K I field IA, then K flux is constant, but IA equals VA minus IA divided by RA. So the torque equation will becomes like this. Now let's substitute EA equals K flux times speed, K flux IF times speed. Therefore, instead of IE, I can replace this equation. Therefore, the torque equation will becomes K IF divided by RA into VA minus K flux omega. So from this, K is constant and I field is constant, RA is constant, VA is constant. And again, K is constant. This is also constant. And the only variable parameter is speed. Therefore, torque and speed is something constant relationship. So it's a constant, it's a direct, it's a constant relationship. There is no any variable. These quantities are constant. So something like this. So as the speed increase, the torque will decrease, and as the torque increase, the speed will be decreased. Usually, it was the torque that can be decreased when the speed increases. Usually, let's talk about the speed control of shunt DC motor. So, from the basic equation of the speed, this is the equation of speed, VA minus IRA divided by KIF. So, from this, you can observe that it depends on the armature parameter as well the field parameter. So we can control the speed of the motor by field control method or armature control method. We'll see each one by one. So each method can be implemented in such a way that either through variable voltage or through a variable resistor or by inserting a rheostat in series with the either the armature in series with the armature winding or in series with the field winding. So let us see the field control method first. I mean the armature control first. Let us see the armature control method first. So at no load, since the value of IA is negligible, because if there is no any load connected to the motor, so the value of IA is very small, very small. So as a result, the value of IARA will be can be negligible. So we can neglect this value. Hence, the speed depends on VA divided by K times IF. From this, KIF is constant, so the only variable parameter we can vary is VA. So we can vary VA from 0 to up to the rated speed, I mean the rated voltage of the machine. So if we kept increase at VA is 0, the speed is 0. If we keep increasing the VA and speed also proportionally increase, but the problem is we cannot go beyond VA rated. So if the rated voltage is say 200 volt, so the maximum voltage that we can increase is up to 200 volt. We cannot go beyond that one. That means in other way, we can increase the speed up to some speed level. We cannot increase beyond that. So usually the armature control method is used to reduce or used to decrease the speed of the machine, not to increase them, because it is impossible to increase beyond some speed level. So that's why usually the armature control method is implemented to decrease the speed of the machine. So if you want to decrease the speed of machine, or if you want to operate your machine at low speed, so armature control method is an ideal method. So you can increase the voltage either by auto transformer, or you can insert a rheostat in series with the armature winding. So this is the armature control method. And let us see the second type of control method, which is a field control method. And again, from the back EMF equation, back EMF equals KIF omega. So from this, you can determine omega. Omega equals EA divided by K times IF. And again, here, the parameter that we are planned to vary is the field current. So we can vary the field current. So as the field current increase, the speed will be decreased, or as the field current decrease, the speed will be increased. Now from this, again, we have a rated field current here. So there is a limit. So we can decrease the field current up to 0, but we cannot increase the field current beyond the rated field current value. We cannot go beyond that one. So that means if we keep decreasing the field current to 0 and we are increasing the speed, because as f approach to 0, the speed approach to infinity. Therefore, the field control method is used to increase the speed of the DC motor. So if you want to increase the speed of the motor, or if you want to your motor to work at a very high speed, so field control method is an ideal method to increase the speed. But here it is very difficult to decrease the speed. To decrease the speed, we have to increase the field current beyond some rated value, which is impossible. So usually the armature control method is used to decrease the speed, and the field control method is used to increase the speed. So these are the two methods applied to control the speed of the DC motor. Now let's come to see the series DC motor. And here in this also, in this part, we are going to see the analysis. The starting of the series motor is very important. And we are going to also see the performance characteristics and the application of series motor. So let's get into it. And in series motor, it is a part of self-excited, and the terminal voltage is connected to both the field part and the armature part. But both the armature and the field are connected in series. So in this case, if you want to compute the analysis, the DC analysis, terminal voltage equals EA plus IA into RA plus RF. But here, since this is a series circuit, IA, the armature current, and the field current are similar. So these are the same. Let us come to see the starting method of the series DC motor. Now, the problem of the series DC motor is, now let us see from the torque equation. This is the equation of the torque, K flux IF. Now, in series, since IA is exactly equals with IF, so these are the same. Therefore, this equation can be written in such a way that KIA square. Now look at it. At the starting of any motor, the starting current of the motor is very high in normal circumstance. It's very high. It is up to 200, up to 500% of the rated current. Now look at here. IA is square. That means now in case of series DC motor, the current will be the square of the starting current. That means, say, if the starting current is 5 times that of the rated current, now the torque at the starting torque, the torque will be 5 square times. That means it is 25 times the rated current, which is very, very, very high. So it is completely impossible, or it is forbidden to start a DC motor without a load. So always when you start a DC motor, be sure that you have connected a heavy load or a load, a rated load to the shaft. So unless and otherwise, the dangerous torque and the dangerous speed at the starting will damage the motor itself. So it's very, very, very dangerous. So at starting of the series motor, be sure that you always connect a load. Then you can start the motor. So otherwise, very difficult to start the series motor. So this is the starting precautions of series DC motor. Now let's see the characteristics of the series DC motor. The first, let us see the speed versus armature current characteristics. So this is a speed equation. And again, if armature voltage is constant, the RA and RF are constant. This is constant. So the only parameter are IA. But let us simplify the equation first. Let us simplify it. VA divided by KIA, this is minus, so IA is cancelled by IA, therefore RA plus RF divided by K. So this quantity is purely constant, and this are constant. So from this we can see that the speed is inversely proportional with the armature current. So the curve of armature current versus the speed is something like inversely proportional. So this is a speed versus armature current characteristics. So as you can see here also, at starting the IA is very high, so the speed is infinity. So it's very dangerous to start a DC series motor without load. And the second part is the torque versus armature current. So from the torque equation, torque equals KIA times IF, but IA and IF are the same. So torque equals KIA square. So the relationship between the armature current and the torque will be something the square parabolic equation. So this is a developed torque and this is a shaft torque. Thirdly, let us see the torque versus speed. Again, from the speed equation. So VA into IA RA plus RF K times IA. So torque equals K times IA IF. So the speed will becomes VA IA this quantity from the speed equation, this is a speed equation. So we know that the torque equals KIA IF. Therefore, we can replace this quantity, K times IA equals torque divided by IF. Therefore, this is torque, then this is IF. So when you see the relationship between the speed and the torque, it is again inversely proportional. So when it comes to the application of series DC motor, series DC motors are used for application of a very high starting torque, like elevators and cranes. And series motors are suitable also for the application where the load on the motor is permanently connected. And thirdly, series DC motor is not suitable for a load driven by belt, because sometimes the belt might be failed, so it's very difficult. The main disadvantage of the series DC motor is the motor speed depends on the load, and the speed regulation is quite poor, like the case of other DC motors. Now let's see a problem. In this problem, 500 volt DC shunt motor had an armature resistance of 0.06 ohm and the field resistance of 100 ohm, and the speed of the motor is given in revolution per minute, which is 750, and also the motor constant is given 1.2. So the required parameter is the input and output power. So this is the equation, the equivalent circuit, I mean. So this is the input voltage. This is a field resistance, it's shunt winding, and this is the armature resistance. So from this, we can determine IF first, because IF equals V in divided by RF. So it is about 5 ampere. And let us convert the speed into it is given in revolution per minute. Let us convert it into rad per second. So using this equation, so the speed becomes about 78.54 rad per second. So speed equals E by back EMF divided by I field times constant. So back EMF divided by I field is we have obtained 5 and the machine constant is 1.2. So you can easily determine the back EMF simply by multiplying this speed by the IF times K. So the back EMF will be 417.23 volt. And now we can determine the armature. So the armature equals armature current. The armature current equals VA minus EA back EMF divided by RA. Now we have VA, we have IA, and we have RA. So the armature current will be this much. Therefore, now the output power will be the back EMF times IA. So we have a back EMF, we have IA. So we have this amount of output power, or we can multiply the torque times the speed. That will give the output power. Torque is K times IA times IF, and speed is as it is. So if you multiply also, you can get the same result. Now, the input current equals the total input current. To determine the input power, the input current will be IA, that we have been obtained, plus IF, that's 5. So totally, the input current is 484.5 ampere. Therefore, the input power will be input voltage times input current. The input voltage is 500. The input current is this much, and the input power will be 242.25 kilowatt. So this is the input power. We have already determined the output power, which is 225.95. So if you want to compute the efficiency of the motor, the output power is this much and the input power is this much. So it is about 93.27%. So with this, we'll end our today's lesson, and next time I'll meet you with another video. So have a nice time. Don't forget to subscribe and comment and like the video. See you. Bye-bye.